All right, so today we have a little video dealing with sound, and then we're going to be talking about strings, particularly, and how they produce certain frequencies, and then the names and the vocabulary associated with these frequencies. So let's begin with sound. So, sound deals with a longitudinal wave. So, longitudinal waves have areas of very high pressure. So if these little balls are air molecules, you'll find areas where it's really stretched out, and then areas where it's very compressed, and then stretched out again, and then, of course, compressed. And we get a regular repeating pattern, or simple harmonic motion. So we get areas where the pressure is high, and areas where the pressure is low, and then high, and then low, and then high. And so if we graph pressure versus time, you can see that we result in a wave, and the wave has this regular repeating pattern of high and low pressure. And so, sound, in its simplest form, is air that has been compressed and then stretched. Physics types like to use the word rarefied. So they'd say, here we have compression, here we have rarefaction, compression, rarefaction, compression. Now, sound can be made by different things. It can be made by stringed instruments. It can be made by pipe instruments. A guitar is an example of a string instrument. And then like a horn of some kind would be a pipe instrument. And the pipes can be open or they can be closed. And what we're going to look at today are stringed instruments. So when we deal with stringed instruments, we'll have two posts which are not going to be able to be moved. So two immovable posts, and we're going to stretch a string in between. So similar to a guitar. So when you stretch the string between the two posts and you pluck the string then gets some kind of undulation, some kind of energy is created, and then that energy or that wave moves across, would hit the other side and come back upside down, and then hit here and then come back forward, but it would have a certain speed. And so we can find that speed by knowing a couple things. Some of the things that we'd have to know to find that speed would be like, how tight is the string in newtons? How much mass does the string have in kilograms? Usually they give it to you in grams though, and then you can convert over to kilograms. And then what is the length of the string? So like, how long is the string? And usually that's given to you in centimeters, but you want to turn that into meters. So with tension, mass, and length, you can determine how quickly a wave can travel through a string. So here's the formula that relates these things. So tension is equal to the mass divided by the length times the velocity squared. What we need to do is we need to rearrange this in terms of velocity. So you would bring up the length and bring down the mass. So tension times length divided by mass, and this was squared, so we end up square rooting it. And you could go through and you could solve for the velocity of a wave in a string. Now there's other ways to get velocity as well. Like we did before when we studied simple harmonic motion. You can find the velocity of a wave by taking its frequency times its wavelength. So we're going to use both of these when we go through and do a problem like this. So let me give you some information about this particular string. This particular string that we're going to be studying is going to have a mass of 7 grams. 70 grams, sorry. And it's going to have a length of 40 centimeters. Sorry, I thought the camera wasn't working, but I'm getting a weird screen here. All right, better. 40 centimeters for the length. And then finally, we also have a tension equal to 12 newtons. So I was kind of looking at the problem set and coming up with some numbers based on that. So what do we do here? How are we going to solve for the velocity in this particular string? Well, we're going to begin with our formula. So our formula that we just left off with, V is going to be equal to the square root. Now we're going to put our tension in, 12. Now before I put in my length, I've got to convert. So that's going to be 0.4 meters. 40 centimeters is 0.4 meters. Got to get the units to meters. And then we divide by our mass. And we got to go from grams to kilograms. So we end up with something like this that we can then plug into our calculator. This is going to tell me how quickly this wave will move across this string of this length, of this mass, and this tension. So 12 times 0.4 divided by 0.07 square root. 8.28. Let's just say 8.3 to make it easier on ourselves. That's the speed at which the wave can move across the string. So here's the wave moving across. That's the speed. Now, what happens is when you actually pluck a guitar string or a string, that string will vibrate and it will create something called a standing wave. And when you pluck a guitar string, you actually get a very complex mixture of what we call standing waves. So I'll get this happening, and this is just how the wave is kind of, or the string is kind of vibrating. So it creates a way that it doesn't move on the ends, but it also forms this weird thing in the middle called a node, where it doesn't move at all. And then this could happen too. And you could add an additional node to the ones that we already had. So now this one would have 1, 2, 3, 4 nodes, where the last one only had 3. And you could get something like that happening. So when all these things are happening at once, we call these different standing waves you produce harmonics. So they have to have names. And so the first one I showed you looked like this. This was the longest wave possible. And we would call this its first harmonic. So the first harmonic looks like this. In fact, if I asked you how long this wave was, you would have to continue this to see the complete wave. And it would like come over here, and then you would be like, oh, there's a wave right there. But it's showing all the possibilities. So we would say that the first harmonic for the string, we see half a wave. So the length of the string equals 1/2 of a wave. We could turn that around algebraically and say wavelength equals 2L. This is always the case for a string for its first harmonic. The first harmonic can also be called the fundamental frequency, FF for short. And then we can figure out how many hertz it would have eventually. So when we're talking about wavelength, we call it its harmonic. When talking about frequency, we use hertz. The next one I drew looked kind of like this, where I had a node in the middle. I had the part of the string which wouldn't move at all, and that's happening at the same time as well. And you would generate something that looks like this. We would call this well, let's look at the formula first. That might explain it a little bit better. L is going to be equal to 2/2 waves. So wavelength would equal L. And when I go to describe this, last time I looked at the number up here and it was 1. Now if I look at the number up here, it's 2. I would call it its second harmonic. And it would look something like this. Wavelength equals L. Now if we come over here, we would call it its first overtone, OT for overtone. The first overtone is the same as saying the second harmonic. And so for this example, we could also find out its frequency. And the last thing that I had drawn looked like this. And we'd add an additional node in. And so we would get a wave that looks kind of like this. You might be saying, well, what is that? Well, that's where we see one wave plus another half. What would that be? That'd be 3 halves of a wave. Therefore, wavelength would be equal to 2/3 L. And so we would say that this is its third harmonic. So for strings, it goes 1, 2, 3 for its harmonics. We could also call this the second overtone, and then it would have some frequency associated with it. So it goes 1, 2, 3, first, second, and third harmonic, and then likewise it would go fundamental frequency, first overtone, second overtone. And all 3 of these are happening at the same time. And the mixtures of these different standing waves, the mixture of these different harmonics, give every instrument its own unique sound. So if we were talking about a violin, maybe it relies heavily on the second harmonic. If I was talking about a piano, maybe it relies heavily on the third harmonic to produce its sound. Maybe a guitar relies heavily on the first. So it might be like 80-10-10, or it might be like 40-40-20. You don't know. Every instrument has its own unique mixture. And there's more than just 3 harmonics. It could be 4th, 5th, 6th, 7th, 8th, 9th, 10th. You can take it all away forever, but we're only going to do the first 3. So let's do some of the math here. We knew the length of the string was 40 centimeters. We knew that earlier, right? 40 centimeters long. And we can kind of plug that in for L here. So if I take 2 times 0.4, that would give me 0.8 for my wavelength. So wavelength is going to be equal to 0.8. I can find the wavelength for the next one. Wavelength equals L. Well, that's easy. 0.4 meters for the second harmonic. For the third harmonic, I would say wavelength equals 2/3 L. 0.66 times 0.4 gives me I better use a fraction or else it won't come out perfect later. So 0.667 times 0.4. 0.26 repeating. 0.27, good enough. And you can see the longest wavelength was the first harmonic. Now if we take these wavelengths and we use our velocity that we found earlier, remember the velocity that we found earlier, if we look back here, was 8.3. We also had an equation that we used to find that, but I said there's another way to get velocity as well. So if I put 8.3 in for the velocity, and I now know my wavelengths, I can find each of these frequencies. So what we're going to do is use that formula. We're going to use it 3 times. So V equals frequency times wavelength. Each time we're going to solve for frequency. So remember, our velocity was 8.3. It's not going to change for this string at this tension with this mass. And we'll put in our wavelengths. We said the wavelengths were 0.8, 0.4, and 0.27. 0.8, 0.4, and 0.27. And we're going to just solve for each of these frequencies. Remember, each frequency has its own unique name. So I'm going to take my speed, 8.3, I'm going to divide by 0.8, and that's going to end up giving me my frequency. So the first frequency I get is 10.4. So the first harmonic's frequency is 10.4 hertz. Let's do it for the first overtone now. So we're going to take 8.3, and then I'm going to divide it by 0.4. I get 20.75. So let's just say 20.8. Let's do it one more time here. 8.3 divided by 0.27, and that wasn't exact, but good enough. And we get 30.7. You should see that it's going up each time. goes up a little bit more each time. Maybe one of these days I'll get the right color. 30.7. All right, so time to evaluate why we call these things what we call them. The first harmonic or fundamental frequency was 10.4. Then we had the first overtone or second harmonic. Look at the frequency. When we find the second harmonic, its frequency is always twice as high. 10.4 became 20.8. When we find the third harmonic or second overtone, it is always going to be 3 times as high. So that is how we approach a problem with a string. There's a lot of vocabulary here. We learned that sound waves are longitudinal, right? We started with that. We said, hey, sound waves have high and low pressure. They make a wave that looks like this, a longitudinal wave. We found out that if we want to find the speed of a wave, it matters how much mass the string has, how much the length of the string is, and the tension of the string. And we could plug it into a formula, and we could solve for the velocity. We did that, and we got a velocity to be 8.3. We said the string can set up standing waves. The 3 longest standing waves it could set up would be the first harmonic, the second harmonic, and the third harmonic. We can look at the waves that they're creating, and we realize that it's 1/2 of a wavelength, 2/2 of a wavelength, 3/2 of a wavelength. Rearrange algebraically, 2L, L, and 2/3 L. Plug in the length of the string, find your wavelengths, use our other velocity equation, frequency times wavelength, and then solve for the frequencies. The longest wave gives you a fundamental frequency. The second longest wave gives you the first overtone, and the third longest wave gives you the second overtone. And so this is how we approach a problem like this. All right, the end.